Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to YouTube channel Chandan Physics. In this video, we are going to discuss electromagnetic nature of light, definition and properties of wavefront. Let's begin. Electromagnetic nature of light. First of all, a hypothesis which is known as ether hypothesis was introduced as the total universe is made up of ether and that luminiferous ether is elastic in nature. That is why light can propagate through that of luminiferous ether, and the concept of geometrical optics like reflection, refractions are well understood by using this theory. But further phenomena like diffraction, polarizations are not easily explained by using this concept, or we can say by using that particular luminiferous ether theory. But to overcome that hypothetical medium which is known as luminiferous ether, when Maxwell sir come to picture, he introduced a new theory, that is the electromagnetic theory of light. By using the electromagnetic theory of light, we can easily explain various phenomena related to light. So, what be the electromagnetic theory of light as proposed by Maxwell? According to this theory, light travels in the form of electromagnetic waves, in which both electric and magnetic field vectors are mutually perpendicular with each other, and both of them in turn are perpendicular to the direction of propagation of these waves. What exactly the theory indicates? In this direction, let electric field vector that direction the magnetic field vector, that be the propagation of wave, direction of propagation of wave. So, the electric field vectors are looking like this. The magnetic field vectors, which also perpendicular to the direction of propagation of that electric field vector. So, that are the magnetic field vectors. Both electric field vector and magnetic field vectors are mutually perpendicular with each other, and that axis gives the direction of propagation of wave. What is the velocity of this wave? The velocity of these waves in a medium depends upon the electric and magnetic properties of that of medium. So, the velocity of these waves in free space, velocity of electromagnetic waves in free space, or we can say that is the vacuum, which is equal to the speed of light c 1 divided by under root of mu naught epsilon naught. Where mu naught, that is the magnetic permeability of free space. Similarly, epsilon naught is the electric permittivity of free space. So, in similar pattern, the velocity of that electromagnetic waves in a given medium can be expressed. Similarly, velocity of electromagnetic waves in a given medium so let v be the velocity of that electromagnetic wave in that given medium, which is equal to 1 divided by under root of mu into epsilon, where mu with the magnetic permeability of that medium, epsilon is the electric permeability, electric permittivity of that medium. Here mu magnetic permeability of that medium, epsilon the electric permittivity of that medium, the medium through which electromagnetic wave propagate. That will be the expression for velocity of that electromagnetic waves. So, with the help of this electromagnetic theory of light, which was proposed by scientist Maxwell, that is successful explaining the optical phenomena like reflection, refraction, diffraction and polarization. These phenomena are easily explained by using the electromagnetic theory of light, but it does not explain some phenomena like photoelectric emission, Compton scattering, absorption and emission of radiation. Absorption and emission of radiations can't be explained by using electromagnetic theory of light. These are some basic properties of electromagnetic nature of light. Now, we study about definition and properties of wavefront. According to wave theory of light, as we discussed, a source of light sends out disturbance in all the directions in a homogeneous medium. Homogeneous in the sense throughout that of medium, we can say either the refractive index be same, or we can say the magnetic permeability or electric permittivity must same throughout that of medium. That is why we can say that be the homogeneous medium. The disturbance reaches all those particles of the medium in phase, which are located at the same distance from the source of light. Hence, at any instant, all such particles must be vibrating in phase with each other. So, how we define the wavefront? So, the locus of all particles of the medium which at any instant are vibrating in the same phase is called the wavefront. Let me understand it. Let me consider a point source of light. S be the point source of light. From that source, light emitted, which sends out waves in all directions in a homogeneous isotropic medium. And the medium is assumed as homogeneous and isotropic. Isotropic in the sense in all directions the speed of light, or we can say the velocity of light, will be same. The waves travel through the medium with the speed of light. We can say the speed which is equal to c. After time t, all the waves reach the points, the distance be ct. Again the wave here, the distance be ct. So, all the waves reach the points lying on a sphere of radius ct. After let some time t dash, that wave, these wavelets, a portion of that wavefront is known as the wavelet. These wavelets reach the sphere of radius ct dash at a distance here. Let time taken to reach that point be t dash. So, again the locus of all points vibrating in that of same phase. Let A2, A1, A2, B1, B2. Again after some time the locus of all points vibrating in the same phase be considered as C1, C2. Now, the surface of the sphere, we take it ct as radius, draw a sphere. So, this line represents the surface of the sphere. Imagine it in 3 dimension. So, the surface of the sphere at a particular instant, this at an instant of t, that at an instant of t dash, again at a particular instant we get that surface of sphere that represents the wavefront at that instant. These are the wavefronts. That one is a wavefront, that one is also a wavefront, this is also called a wavefront. So, these are the wavefronts. So, according to the definition we can understand what be the exact scenario of wavefront. Now, various types of wavefront. The types of wavefront basically depending upon the shape of the source of light, from which source light emits, that represents what should be the type of that particular wavefront. So, according to the nature of that source of light, it is classified as first one spherical wavefront. A spherical wavefront is produced by a point source of light. If the source of light just like a point, because the locus of all such points which are equidistant from the point source is a sphere. Look here, that be the point, light from that point emitted. So, locus of such points imagine it in 3D, that the source of the light, that wavefront is the spherical wavefront. Now, the concept of cylindrical wavefront, another type. A cylindrical wavefront is produced by a linear source of light. If the source of light is from a line, we can say it is a cylindrical wavefront, because all the points which are equidistant from the linear source lie in a surface of a cylinder. Here all the points lie in the surface of a sphere, here all the points lie in the surface of a cylinder. So, it is look like a cylindrical wavefront. Look here, let that be the line source. Now, the equidistance from the line source is drawn like this. Again same thing here. That look like a cylindrical wavefront. This arrowhead represents the direction of light. Now, plane wavefront. If we consider a small part of a spherical or cylindrical wavefront which are originating from a distant source of light, will appear a plane, and hence it is called as the plane wavefront. If we take a small portion on that of sphere or on that of cylindrical wavefront at a particular distance, it seems to be like a plane. It just look like a plane here. That is the representation of a plane wavefront. Now, some properties of wavefront. An arrow drawn normal to the wavefront and pointing in the direction of propagation of light represents the ray of light. This arrowhead represents the ray of light. These are ray of light. That is the direction of propagation of light. In this figure, the arrowheads represent. And that ray of light is nothing, that is the path along which light travels. Look at the figures. In case of spherical wavefront, cylindrical wavefront and plane wavefront, these arrows represent the rays of light. These are the rays of light. And now we draw some figures for plane wavefronts. In case of plane wavefronts, these are the plane wavefronts. These are the plane wavefronts. These arrowheads represent the rays of light. These are the wavefronts of a parallel beam. Now, if S be the source, the beam of light are converges. So, the wavefronts are represented like this. These are the wavefronts. These are the spherical wavefronts. Spherical wavefront due to that converging beam. And again, in case of diverging beam, let that source S, beams are the light beams here diverges from that source. So, the wavefront as that particular case, these are the spherical wavefronts. These are the spherical wavefronts when the light beams are diverging in nature. When the light beams are converging in nature, these are the spherical wavefronts, and if the light beams are diverging in nature, that the representation of spherical wavefront, and when the light beams are parallel in nature, that the representation of plane wavefronts. So, with the help of this visual expression, we understand electromagnetic nature of light, definition, types and properties of wavefront. So, with this useful and informative notes, let me wind up this session. Thank you.